The reason we do material balance is because we need to quantify things. We need to make sure that, we need to know how much of a particular substance is actually entering or going out of a system or actually remaining in the system. So we need to quantify, we need to give value on those environmental systems. And it is important to do material balance because without doing this, we'll not be able to know exactly or to identify what process to do for a particular instance. Like, for example, we're looking at wastewater treatment, all right? We need to know how much pollutants are actually incoming and what is the desired goal of water chemistry or water quality we are trying to do so that we can balance out in the treatment process. Okay, what sort of treatment processes we have to include in the system, if we are going to include some flocculation, if we are going to include some coagulation there or some filtration, so that we'll be able to, to know the materials that are coming in and coming out and also remaining in the system. All right. So this is good for important tool, the material balance or the mass balances. And when we say material balance, we are referring more two things, the energy balance as well as the mass balance. And in most cases, it's about the mass balance. So we can have some modal production of the pollutants in the environment, like for example, in the groundwater, how long will the pollutant from point A to point B, how long will it reach the point B? For example, point B is your home and the point A is the source of the pollutant. How long will it travel, the travel time? So we can calculate some mass balances there. Reactor treatment design of wastewater, air pollution, filtration. So these are part of the reasons why we need to understand the concept of mass balance. Even the equipment design. So we need to know how much are coming in, how much is coming out. And also it is related to the profit or to the budget, for example. Because without doing initial calculation of mass balances, it's not easy to design something because you don't have a basis of the value of the coming in and coming out. So these are a form of mass balances. If you can look at this figure here, if you look at here, there's a big gap. It's a wide drawing. So it means that the initial input is big. Like for example, the green one is more of the mass. The orange one is more of the energy, and the blue one is more of the water. So as you go towards here, the sizes of this drawing is changing because it's going out and some are going in. So the amount is also changing. So if you have a very high, it's a big amount here coming inside, and then suddenly it becomes big as well as coming out, it means something is transformed or there's a production inside the system. So we need to know this kind of material balances in order to understand more of the whole process. Right, so this is there are two theories that we need to know. The first one is on mass balance. This is the law of the conservation of energy or matter. So matter can neither be destroyed or created. Energy is also a use of a law of conservation of energy. It cannot be created nor destroyed. It can only transform from one form to another. And we'll be discussing this energy balance in next week as well. For today, we're talking about the law of the conservation of matter. All right, so these are the different of the various mass balance applications, and for environmental engineers, civil engineers, it's very important, especially in water treatment systems. So you have water treatment systems like this part here. We have the even the whole hydrologic cycle is also mass balance, right? If you like the hydrologic balance, the water is evaporated, it goes towards to the atmosphere, it forms the clouds, and the clouds, precipitates into rain. So it becomes rain here, it goes down again, and so the water seeps through the ground and goes to the groundwater, and then the whole cycle again repeats. But overall, if you compute the overall mass or amount of water on Earth for so long time now, it's basically the same. It's the same amount of water that we have for millions of years. It's just that some water are not usable anymore because they become polluted, but the whole volume and the whole amount is still the same. All right. So this is the hydrologic balance that we have. reactor design is important to do the mass balance concept as well. As I mentioned before, they have water treatment, wastewater treatment, and we will be talking about various types of reactors as well. So we have the batch reactor, we have the plug flow reactor, and we have the completely mixed reactor as well. So these are the types of reactor we're going to discuss next week. Oxygen balance, also important in rivers and streams, because we need to know, for example, in a river, if you dump like this here, in this example. So we have river water here, the stream is flowing and it's flowing down. And we have the upstream here, we have the downstream here. And then if you put pollutants, for example, like a waste, you dump waste here, it means that there are a lot of organics there. And organics will need bacteria, they will be eaten by bacteria, and bacteria need oxygen. So if you put a lot of, BOD, biodegradable organic, materials there, it means that the oxygen content of that specific area will decrease because the bacteria now are using the oxygen for themselves, for growth and for decomposition. And so in that case, the balance of the oxygen on the river will change, all right? So there will be a decrease of oxygen, and if you have a decrease of oxygen, what happens? The fish in the river will die eventually because they need oxygen. So that's why we need to also know the mass balance of oxygen balance in some water, especially if you are trying to dispose of some organic materials there, or some even biodegradable materials that can affect the overall balance of the oxygen in that specific area. All right. So mass balance is just basically like it's like a process of depositing and withdrawing in a bank. It's like a mathematical expression of the conservation of mass. So we need to express this one in terms of an equation, right? Just like in a bank, you put a deposit on the bank, the money could have an interest, it could grow. So in the same case, in our mass balance, sometimes inside that control volume, there is a transformation. There is a production of some other materials, or there is a degradation, so minus. So in this case, it's production, is interest. So there's a reaction there. And then there's an output. So there's an input and there's an output. So in this case, the balance is the accumulation of your money in the bank, this part here. The deposit is your input. Okay, the withdrawal is your output. And the interest is the reaction, is something that is production. So it's very similar with money. So if you try to make it as an equation or express as a mathematical expression, mass balance is mass accumulation rate, okay, is equal to the mass flux in minus the mass flux out plus or minus the transformation rate. It depends. It could be a decay, which is a minus, or a formation or a production of something new. All right. So in this case, the rate means per unit time. So it means there's a time basis. So the amount of the mass that is accumulated per unit time, per second, in most cases. Sometimes it could be days or hours. It depends on you, but these are per unit time for the rate. The same way for the flux. So in this case, we can refer to it as a mass mathematical expression. Okay, the change of mass per unit time is equal to the mass flux in, mass rate, minus mass flux out, and derivative of the reaction per unit time. So the transformation rate. Right. So this is the main equation for mass balance, and you have to remember this equation because this is important. All right. So in engineered systems, for example, environmental systems like water systems, as we mentioned in our units lecture, concentration is there. We refer to a lot of concentrations, especially pollutant concentration, because as environmental engineers, we are dealing a lot of pollutants, a lot of contaminants. And it's either we control the contaminants or we make sure that these contaminants, if it goes out into a system, will not affect the overall new environment. All right. So the mass out will have a safe level of at a safe level. All right. It's not a toxic level. Right. So concentration, as is in the form of C here, is equal to mass over volume, which is in the unit of milligram per liter. And then we have volume flow rate. So volume flow rate is the amount of volume per unit time. All right, so the volume per unit time. So the volume could be in liters or in cubic meter per unit time, day, hours, or second. So the mass flow rate is basically the concentration times the volume flow rate, C times Q. All right, so if you look at here, C times Q, mass over volume. So this is mass over volume, this is volume over time. So what happens? It will cancel out. All right, so the volume will cancel out. What will be remaining is mass over time. So that is mass flow rate. So milligram per liter, liters per day, milligrams per day is now the unit. And you need to be careful with units because this is important. So milligram per day or milligram per second or milligram per hour, doesn't matter. This is what we call as the mass rate. In terms of if you are not given with the rate, you are given with a fixed mass or a volume. So if you have a concentration, then you multiply with a volume, you can get the mass, not the rate, not per unit time, but still the same. So C times V is mass, Q times T, which is volume flow rate times the time, is equal to the volume, the amount of the volume of that particular area, all right, or the particular control volume. So you can example from here. This is an example of a mixing vessel. We have a control volume. This is a control volume here. So when we say control volume, it's basically the area that you have interest with, where the mass balance will occur. So you have an input and we have the output and we have the accumulation. So if we put the control volume in this part of the mixing vessel here, once we have a CV that's a control volume, we can now identify what are the inside and outside, what is coming in and what is coming out. All right, in this case, mass in is spent acid, concentrated sulfuric, and concentrated nitric acid going to this control volume, and there is a product as an output. All right, so you can have that as a mass balance concept here. The same way, if you have a reverse osmosis filter, so if you have a filtration here, you have a mass in, you have a mass out, and you have another mass out here. So if you get the control volume from this side, you can only get 2. If you get the control volume for the whole RO unit, then you have 3 cases: mass in, mass out, and mass out. All right, and we will be giving you more examples on that one. All right. So in this case, the reaction rate is basically the amount of concentration per unit time that is either decaying or is either increasing or producing. All right. So for example, if you have kinetics, for example, if you are degrading dye solution, so the amount of dye in that particular container will decrease because you are trying to degrade the dye. So it means the reaction rate is always increasing. It's always a positive value, but the amount is decreasing if it is decaying matter. If it's decaying, if it's producing, then it has to increase as well. All right. So with that, we can rewrite this expression. As I mentioned earlier, accumulation, mass accumulation here, mass flux here, mass out here, and reaction. Rewriting this one, we can have CV, okay, the change of CV over dt times CQ in, CQ minus CQ out plus minus RV, which is the reaction rate times the volume. All right. So if you calculate all of these are all mass rate. Mass, all right? This is kilogram per second or kilogram per day. The same way, this is kilogram because, concentration times volume. Concentration is milligram per liter, right? Times volume is milligram. Then dt is time, which is second or day. So milligram per second, so it's the same. So all units are the same here, all in mass rate terms, milligram per second, more or less. All right? But in most cases, the volume of a specific reactor is constant. It's not changing. So this is constant here. The volume is constant. So we can have the volume as outside here and only the concentration of a particular substance inside the reactor is changing. All right. So volume is constant. So changing concentration, and then we can now solve for the overall mass balance here. All right. When we talk about mass balances, we talk about various pollutants as well, as I mentioned. And one of the things that is a good assumption as well is to use these called as conservative pollutants. these conservative pollutants can make our the solving of a problem easier, because this refers to a system or pollutants that has no or that have no reaction that is occurring in the system. Right? There's no reaction that occurs in the system. So it means that the pollutant does not decompose or regenerate. It doesn't add or it doesn't degrade. All right? So that's why it is termed as conservative. The amount is conserved. It's the same. All right? So what goes in equals what goes out. So in this case, in most cases, the good example are heavy metals. If we are talking about heavy metals, like the metals of manganese, we have other metals that are in the system, all right? Then cadmium, lead, that are also easy to identify in the whole system. These are considered as conservative materials or conservative pollutants, all right? So if we are talking about conservative pollutant, what happens then to the mass balance equation? As we know, this is the mass balance equation, as you remember. If we say that we are dealing with conservative pollutant, it means that there is no reaction. So this part here becomes zero, right? So now the transformation rate is zero. So now here is zero. So now it makes the equation, simpler. We have only the mass accumulation, mass in minus mass out. Okay, so that is for the mass balance for conservative pollutants. All right. And then we have another condition. Aside from conservative pollutants, we have a condition what we call as steady state. A steady state condition usually is there is no accumulation of mass with time. All right, no accumulation. It means that the mass inside the control volume stays the same. There's no more, the rate is not anymore changing. All right, this happens especially if there's a time element. A long time, for example, if you are putting some water in your bathtub and the bathtub is also trying to flow out the water, you did not close the tub, so the water is only constantly flowing out while putting some water, but the flow of the water from the faucet, from your tap, is stronger. It means that at a certain time, the amount of water that is flowing out will have similar amount of the water that is coming in. So it's not, the volume of the water inside the tub will not change anymore. So it has achieved, or it has obtained, a steady state condition. So in that case, there is no mass accumulation rate. So in this case, the part of mass accumulation rate is zero. All right. So we can make it zero here. And if we are dealing with conservative pollutant, we can also make it zero here. So what happens? We only have this equation here as a mass balance equation. So it makes everything simpler and easier if there's some assumption. And this is usually used for many assumption for stable operations, right? So if there's a stable operation, then we can assume such steady state condition, right? But if there is a reaction in the system, then this part here is not zero, all right? So we have to be sure with that one. All right, so what are the approach for solving mass balance equations? So the first one is to identify, we need to draw a flow chart or diagram or schematic and identify the control volume. What are the boundaries? All right, so in this case, example, this is a swimming pool. So if we make it as a control volume, this part is the control volume, the whole swimming pool is the control volume. Then based from that control volume, this control volume here, then we can identify what are the mass inputs and what are the mass outputs. For example, in this case, there's mass input here, there's a mass output here, there's a mass output here, and also there's a mass output here. All right, so you can make that as your mass balance equation. Now, if you look at this part here, okay, if you look at this part here, we can also make a mass balance only in this control volume. So like, for example, I want to have a control volume in this part only, right? This part only. So what are the control volume on this part? So we have a mass in here, we have mass out here, and then mass out here. So we are only referring to this part as control volume, the juncture of your piping, all right? So this could also be part of a control volume if you want it to be that way. All right, so finding the control volume is important so that you'll be able to identify the various components of the mass balance. All right. And then once you identify that one, you need to input some values inside of for each of these parameters that you have, like the inputs, outputs, and accumulation, and then convert all units into a similar units. Do not make calculation if the units are different, because this is the usual case for many students. Sometimes you forget about the units, and different units will have different way of solving the problem, right? So for mass balance concept, we have this example here in the lake. In the lake, we have evaporation coming out. This is evaporation. We have mass precipitation coming in. We put the lake as a control volume. We have water coming from the river going to the lake. And then we have water coming out from the lake going to the river or the stream. We have some part of the water seeping through the groundwater, all right? Some part of the groundwater seeping through the lake. So you can see from here, we have a lot of, processes going on in this case, all right? So in this case, we can make a mass balance based on this control volume as the lake. So by putting a schematic drawing, you can see from here, the arrows are important. And so you can go from here, and then you can make a mass balance based from the various inputs and outputs and accumulation in the system. All right. So this is a good way. Usually, a schematic diagram is very important when you solve a problem for mass balance.